Welcome back to MAAZ Innovative Learning. I am MAAZ. In today's video, we are going to learn about what is an ideal Rankine cycle, sequence of operations performed in the cycle with the help of flow diagram, PV, TS and HS diagrams. This is the sixth topic from the unit Steam Power Plant. Also, there is a playlist that has been maintained. So if you are new to this channel, please go to our playlist. You will find a lot of information. Let's get started. Rankine cycle is the thermodynamic cycle for steam power plant. Many limitations of Carnot cycle are eliminated in Rankine cycle by superheating the steam in the boiler and condensing it in the condenser. As you can see, ideal Rankine cycle is illustrated on the board. 4 processes are involved in the complete Rankine cycle and are different from each other. Each process requires a separate component. Further, the working fluid is water, which exists in liquid phase during the part of the cycle and vapor phase in remaining part of the cycle. If you see the flow diagram, you might observe a small change when compared to the flow diagram of Carnot cycle. That is, compressor is replaced with a pump. Moving on to the sequence of operations, consider 4 points in the flow diagram. Here 4:1 represents constant pressure heat addition process. When high pressured water enters the boiler, initially temperature rises from 4 to 4-. Here 4- is saturation temperature and remains constant during evaporation, that is 4- to 1. 1 to 2 represents reversible adiabatic expansion process or an isentropic process. Saturated water enters the turbine and rotates the blades of the turbine so that the work is produced by the turbine. In other words, dry saturated steam expands through a turbine. 2 to 3 represents constant pressure heat rejection process. Exhausted steam from the turbine or wet vapor then enters a condenser where it is condensed at constant pressure to become saturated water. 3 to 4 process represents reversible adiabatic compression process or an isentropic compression process. Saturated water enters the pump and pumped from low pressure to high pressure. As the fluid is liquid at this stage, pump requires little input energy which is taken from the turbine output or work produced by the turbine. Now let's compare the flow diagram with PV, TS and HS diagrams. In process 4:1, that is constant pressure heat addition process. Here heat is supplied to the system. Pressure remains constant, that is P4 is equals to P4- is equals to P1. All the 3 points lie on a same line, and as the water is converted into steam, volume rises from V4 to V1. Coming to the TS diagram, temperature rises from T4 to T4-. Here T4- is the saturation temperature. Till the water reaches saturation temperature, that is T4-, only temperature of water rises. After T4-, evaporation takes place so that temperature remains constant, that is T4- is equals to T1 and entropy rises from S4 to S1. The input energy or heat supplied can be calculated graphically by using an enthalpy entropy chart, that is HS chart. It is also known as Mollier diagram or numerically calculated by using steam tables. Moving on to the HS diagram, enthalpy rises from H4 to H1 and entropy rises from S4 to S1. In process 1 to 2, that is reversible adiabatic expansion process or an isentropic expansion process. If you observe PV diagram, pressure falls from P1 to P2 as the steam expands in the turbine. So volume changes from V1 to V2 and work is obtained by the system, that is turbine work. In TS diagram, temperature falls from T1 to T2 where entropy remains constant, that is S1 is equals to S2. Moving on to the HS diagram, enthalpy falls from H1 to H2, and as I have said, entropy remains constant. In process 2 to 3, that is constant pressure heat rejection process. If you see the PV diagram, heat is rejected to the surroundings by the system through condenser and pressure remains constant, that is P2 is equals to P3. As steam is condensed to saturated water at state 3, so volume decreases from V2 to V3. In TS diagram, temperature remains constant, that is T2 is equals to T3, and entropy falls from S2 to S3. Moving on to the HS diagram, enthalpy falls from H2 to H3 and entropy falls from S2 to S3. In process 3 to 4, that is reversible adiabatic compression process or an isentropic compression process. If you see PV diagram, work is supplied to the pump, that is pump work. Here pressure rises from P3 to P4 and volume remains constant, that is V3 is equals to V4. In TS diagram, temperature rises from T3 to T4 while entropy remains constant, that is S3 is equals to S4. Similarly, in HS diagram, enthalpy rises from H3 to H4 and entropy remains constant, that is S3 is equals to S4. In ideal Rankine cycle, there is no reduction in pressure during evaporation and condensation. So that's all for today. If you are new to this channel, please do not forget to subscribe and please do not forget to share this video. Thank you so much.